Welcome back to our modules on statics. Today I'd like to revisit that beam problem we just did. Simply because it's so rich, it has so much more information on it, we're going to explore. So let's remember that we have 100 newtons pushing down. It's a 10-meter beam, 50 meters on each side. And what we did last time is we took a free body diagram and we kind of expanded that free body diagram from to the left all the way to halfway through and then all the way over, and it gave us a feel, it gave us an understanding of how forces were being transferred from the applied force to each of the supports. And when we did that, we found that there was shear and there was bending moment. And if you remember, each one had its own characteristics and different ways we could think about it. Well, what I'd like to do today is I'd like to take a different look. I'd like to take a look at that bending moment and think about it a little bit. What we're going to do is we're going to pretend like we're going to look at the end of this beam like this. We're going to look at it, all right? And if we look at it, it's going to be looking at, somewhat of a cross section. Maybe the beam looks something like this. And my question to you is, what's happening here? Now we know that when the bending moment applies, you have compression along the top and you have tension along the bottom. Now if you think it through, that kind of makes sense. See, the compression on the top, tension on the bottom, that causes the whole thing to bend. And there's this one location in the middle that doesn't experience any of those forces. We call that the neutral axis. We'll get that to them in a minute. But first, I want to take a cross section of this. As I look at it, all right, we're going to take a look at our forces. I know that at the very top of it, we have these compressive forces. And we'll say to the left is compressive, to the right is tensile. All right. And on the right, or at the very bottom of this beam, we have this enormous compression force. Now, as this beam moves, as it gets deformed, what's happening is at the top, it's deforming more than at the middle. The further away you are from the middle, the more it's deforming, and it's doing that in a linear way. Well, if it's deforming more, that means the forces are bigger, and the forces increase in a linear way. So we can just feel our way to the point where as we get closer to the middle, the forces gradually decrease until you get to the middle. And at the middle, the force equals 0. That's what's happening in the middle. Here we have compression. Here we have tension. So we have a feel for what's going on in the cross section of that beam. But what I want to know is what's going on with the bending moment. How is that all working? Well, we know that the total bending moment is some amount, let's say m, and up here is 150, but it changes as you move across the beam. Let's look at just this small little area and try and figure out what the small little area is, the bending moment is on that small area. Well, we know that the total bending moment is going to be the sum of all the small bending areas. And if we want to know what the moment is there, we know that the moment is just the force times the distance. So we take the sum of the force times the distance. Moreover, if we look back here at what the force distribution is across that entire piece, across the entire beam, we see that it's much higher at the compressive side, much bigger at the compressive side, a lot smaller in the middle. So we know that it's linear based on how far away from the middle it is. Well, linear is something, so it's linear based on the radius. So we can rewrite that. Delta F is K, and we're going to say K is just some constant that indicates the size of the forces. You can imagine if you're just doing a small moment, the spread of the forces would look like this. If you're doing a huge moment, the spread of the forces would look like this. Well, there's your slope. So it's really just an indication of the applied moment. We're going to take K times the radius, because the radius increases the force, and we're going to do it over some small amount of area. Remember, this whole thing, we're keeping this R. is multiplied by r. If we combine these, we get the sum of k, and remember k is a constant, so we don't have to worry too much about that, r squared delta a. Now you know exactly where I'm going with this. I want to turn this into an integral. So I'm going to take all those spaces, all those delta a's, make them really small, and we're left with an integral k r squared dA. Let's take that constant out. It's not that big of a deal, or it's a constant, so we can take it out of the integral, and we're left with the integral of r squared dA. This factor right here should look pretty familiar to you. It's not quite the same as what we've already learned, but it's pretty close. In this case, this is the second moment, or the moment of inertia. What this tells us is how easily this beam bends. Or another way of saying it is how it resists